Welcome to the Walton Pi. Today we're going to be talking about four key properties of measure spaces, specifically of the measures within the measure space. So if we're given a measure space x and mu, mu satisfies the following four properties. First, mu is monotone. So that means that if E is a subset of F, and both of those are in our measurable sets, so in our sigma algebra M, then the measure of E is less than or equal to the measure of F. Second, mu is subadditive. So that means if EI is a countable collection, then the measure of their union is less than or equal to the sum of their measures. There might be some overlap, so that's why we don't have equality, but we are able to say that the measure of their union is less than or equal to the sum of their measures. We also have continuity from below, so that means that if EI is a nested sequence of sets in our sigma algebra, so EI is a subset of the next one, EI plus 1, so they're growing bigger and bigger and bigger. For every, if that's the case for every I, then the measure of their infinite union is the limit of their individual measures. So that's a very helpful property from continuity from below. And then we also have continuity from above, which has one small change that we have to make. So we say that mu is continuous from above if we have, again, a nested sequence, but this time they are getting smaller and smaller. We say that it's continuous from below if this property holds, and every measure does satisfy this, that the measure of the intersection of all of them is the limit of their measures as long as the measure of the first set, as long as the measure of E1 is finite. Technically, this property will hold. We can redefine continuity from above if we know that one of them becomes finite, but this property does not hold in general if we don't have the mu of E1 being finite. So that's the property of continuous from above. So let's go through the different properties and prove that our measures satisfy this. So let's first check monotone. So let's let E be a subset of F. Then F minus E is in our measurable sets. So further, F minus E intersect E is empty. So then we can have, by the countable additivity of mu, mu of F minus E plus the mu of E is mu of F minus E union E, which is just mu of F. Since mu of F minus E is non-negative, we see that then that tells us that mu of E is less than or equal to mu of F, so mu is monotone. To see that mu is subadditive, let's let EI be a collection of sets from our sigma algebra M. Then we can define FIs to be EI minus the union of all the EIs that came before it. The reason we're doing this is the collection of FIs is a pairwise disjoint collection. Okay, so we have that, and all of them are going to be in our sigma algebra M. So then by the countable additivity of our measure mu and the monotonicity that we just proved, we can say that mu of the union of the EIs is mu of the union of the FIs, because they're the same set, which is equal to the sum of the measures from countable additivity, which is less than or equal to the sum of the measures of the EIs by monotonicity, and so that means that mu is subadditive. To get continuity from below, let's let EI be a set so that the EIs are a subset of the EI plus 1s, and then we are going to define F1 to be E1, and for all i's bigger than 1, Fi is EI set subtraction with EI minus 1. So by countable additivity, that means that mu of the union of the EIs is mu of the union of the FIs, so that's just because they are the same set. Countable additivity tells us that's equal to the sum of the measures of the FIs, which is then the limit, just using the definition of limits, because these are all, at this point, real numbers, so that's the limit of the sum of the mu of FIs, which is the limit of the mu of the union of the FIs, which is going to be the limit of mu of En, and thus mu is continuous from below. So now let's talk about continuity from above. If we're given a measure space, let's let EI be a collection so that the EI plus 1s are contained in the EIs, and we're also going to let mu of E1 be less than infinity. So define Fi to be E1 minus EI for each of our i's. And so note that for all i's, Fi is going to be in our sigma algebra, with Fi being a subset of Fi plus 1. Then by countability from below, we are able to get that mu of the union of the Fi's is the limit of mu of Fn's. Okay, but then mu of E1 is equal to mu of the union of the Fi's unioned with the intersection of all the EI's. And we are able to break that up into mu of, because these are pairwise disjoint, mu of the union of the Fi's plus mu of the intersection of the EI's. Since Fi is EI minus, or E1 minus EI, and mu of E1 is less than infinity, we have mu of the intersection of all the EI's is mu of E1 minus mu of the union of the Fi's, which is mu of E1 minus the limit, as n goes to infinity, of the mu of Fn's, which we can rewrite a little bit so that we have some nice things cancel. So our mu of E1's cancel out, which gives us just the limit of our mu of En's. So we have continuity from above. Note that the reason we need mu of E1 to be finite is so that we are able to actually cancel mu of E1 minus mu of E1. Otherwise we are unable to actually do that cancellation. So we do need the condition for mu of E1 to be finite. For example, you can look at the intervals n to infinity, where n is a positive integer. For each n, the measure of that is going to be infinite, but the intersection of all of them is empty. So in that case, the measure of their intersection is 0, but the limit of their measures would be infinite. And so that's one example as to why we need, for continuity from above at least, that mu of the first one be finite. I hope this video was helpful. If it was, please like and subscribe. It helps me to keep making these videos and also helps me know which types of videos I should make more of, as well as leaving comments below. That's a very helpful thing, especially if there are specific topics you would like to see me start making some videos on. I hope you have a great rest of your day and good luck with all of your math.